Good morning. This three-part video series is about constrained optimization from Calculus 3. This is where we have a function, perhaps of multiple variables, where the inputs are constrained to a region, and we want to find the largest and smallest possible output values of the function over that region. Before we do this, we need to discuss the geometry of the input space. This will be crucial to solving these problems since a max or min can occur on the interior of the region or a boundary, and there are actually multiple kinds of boundaries. In Calc 1, this was pretty simple, but in Calc 3, there are many more pieces to analyze. This video will go over the geometry analysis, Part 2 will cover a Calc 1 review example, and Part 3 will cover a full Calc 3 example. To get to the other videos, you can use the links in the description. All right, so let's take a look at how shapes are constructed in n dimensions. We'll start small. What kind of objects are there in 0 dimensions? Well, there's not much space in 0D, so the only object we can have is a point. So I'll draw a point, say up here. That's really all we have. It has no width, no height, no depth, no length, or any other measure we can think of. So what is this point made of? Well, there's really only one piece to the geometry. It's just the point. I'm going to call this a vertex, which is a zero-dimensional piece. So zero-dimensional object is made up of a zero-dimensional piece called a vertex. We're starting small, of course, here, but we'll use this to build higher dimensional objects. Okay, so next, what kind of objects are there in 1 dimension? Well, there's a few possibilities now, but in general, we have line segments. That is a line with 2 endpoints. If it only has one endpoint, we call that a ray. If there are no endpoints, we call that a line. And if there's 2 endpoints, we call it a line segment. So same as before, what is this line segment made of? This time it has multiple vertices. 2 in this case, because those are the endpoints. So 2 vertices. And it has one interior, which I'm going to call an edge. And this is a one-dimensional piece this time. Pretty simple so far. Next, what kind of objects are there in 2 dimensions? We have a lot of choices now. In general, we call these polygons, perhaps a square, for example. So we'll draw a square here. There's a square. Now in Calc 3, you might have a region bounded by a couple of curves, maybe a parabola and a line, for example. It might look like lots of different things, but in general, they are constructed the same way as before. You still have vertices, actually. So square in particular has 4 vertices. You have edges. There are 4 edges in that case. And then you have an interior, which is 2-dimensional this time. I'll call that a face. One face, and that is a 2-dimensional piece. I'm sure you can see the pattern by now. We can extend this to as many dimensions as we want. I'll do 3 dimensions just for fun. Based on the pattern, it would make sense that 3-dimensional objects have vertices, edges, and faces, plural. And then it's going to be made up of one interior, 3-dimensional interior, which I'm going to call a cell, which is 3-dimensional. And a good example of a 3-dimensional object perhaps is a cube. There you go. And we can see from this drawing here, it's got vertices. Has what, 8 of them? It has edges. I believe there are 12 of them. There are 6 faces. They say front and back, left and right, and up and down faces. And then one interior, which is 3-dimensional. So I'm sure you can see the pattern by now. Every n-dimensional object has an n-dimensional interior and is made of every kind of piece in lower dimensions. We can call these, say, it's always got, if it's nd, it has n-1d pieces, n-2d pieces, and that goes all the way down to 3d, 2d, 1d, and also 0d. Those would be the vertices. So I'll say that once again, every n-dimensional object has an n-dimensional interior and then is made of every kind of piece in lower dimensions, all the way down to 0 dimensions. There are some exceptions, of course. You might have, say, a circle, for example. I don't know. Circle is 2-dimensional but doesn't have any vertices, perhaps. So if you have curves, you don't necessarily have all those pieces. But that's in general what you want to look for in these Calc 3 problems is all of those different pieces of geometry from ND all the way down to 0D. So why is this important for calculus? Again, we're looking at optimizing functions. If you've been through Calc I, you're probably used to setting the derivative equal to 0 to find critical points and then testing the ends. Well, this is the one-dimensional case. The derivative tests the interior, and then you have to test the vertices separately. The difference in Calc III is that we're dealing with functions of multiple variables. The reason we had a one-dimensional space before is because that is the input space. So for this one, if I say f of x, do x in red, like that. F of x only has one input variable, so the input space is one-dimensional. On the other hand, if I say f of xy, so now say we have a function of two variables, that input space is two-dimensional. And of course, this extends to as many dimensions as you want. Say f of xyz, for example, would be a three-dimensional space. You can keep adding them. F of xyzw perhaps would be a four-dimensional space, which is harder to draw, but the geometry extends in the exact same way as we had before. So in Calc III, when we're optimizing f of xy over a region, that region will be two-dimensional and therefore has an interior, edges, and vertices. That's the idea there. We test the interior by setting derivatives, plural, equal to 0, just like we did before. We can test the vertices by plugging numbers into the function, just like we did in Calc I. If we stop there, we ignore the edges. That would have tested the face and the vertices, but not the edges. There's a special way we test the edges, which we'll see in an example later. It's certainly possible for a max or a min to show up on an edge, so if we ignore them, we could easily get the answer wrong. So with that, let's jump into a Calc I example for review. I'll see you guys in part 2.